Shall let's do this. All right, so we are now recording. And so we are starting, basically we were done with the first third of the semester. Now we're in the second third of the semester. This is actually the most important part. And after this, like the last third is miscellaneous things. So I'm not so concerned about that. It's just kind of like fun, interesting things I'll show you about, as machine learning is very broad, but really I wanted to cover this topic. All right, this is my main one of the most important topics. So we'll be doing PyTorch this semester. So we're switching over to like a very powerful tool. We may also look at TensorFlow, although I don't like to mix frameworks. But yeah, so today we're going to look at these two modules. Okay, this one, performance metrics. So you guys have used some of these metrics already, especially with in terms of classification. Okay, and then I will also look at we'll look at this these links here. In particular, we're going to do these two links. These are two Jupyter notebooks that I've posted on GitHub, and they're very basic, but also very important, right? So we're just going to take a look at what it is, what they mean, and you'll see me coming back to that. It's very foundational. The XOR problem we'll possibly do either on Thursday or next week. It's also very important to understand neural networks. I have some slides, so this is kind of my notes. I'll go over that. And yeah, basically that's the point. But I do want to start with these slides over here, performance metrics. Usually the way that I cover these slides is I do it in two parts. So I'll do the first half today, and then the second half next week. I'll let you like digest some of the ideas before we jump into it. So I think all right, so performance metrics. So you may have some questions here, and I'm sure you've heard of these ideas before. All right, there it is. All right, so we're going to talk about machine learning performance metrics, which you have used, and this is more about where do they come from. So what are performance metrics? So basically is this whole idea of how to measure the performance of a model, right? So you did, and Eric showed us today, the two classification problems and then one regression problem. The difference there was that with the regression problem, we were generating like real valued numbers, whereas with classification, we're generating labels, basically. Now, what about the generative model, your project that you're doing right now? You're generating images, right? What do you think, if you had to just guess, this is a classification or a regression, which one would you say for your mini project? You're generating images, right? You're taking 5 images that you selected of the same size and you average them and create a new image out of that. Is that more like a regression? It's more like a regression, right? So if you think about it, you are doing a kind of a regression. Just it doesn't matter what the underlying mechanism is, a very simple averaging. At the end of the day, you're generating these real valued numbers, okay? Now, neural networks, the thing that we're going to start discussing, could also generate these images. Obviously, they're not going to use averaging and KNN. Instead, they're going to use a neural network. If you've ever heard of stable diffusion, for instance, which is a tool that you can write and it generates an image, similar idea. At the end of the day, that's a n by n, and it's RGB, right? And it's generating images. So neural networks, we're going to be using them for kind of this, to generate things, basically, either classes or regression values. Okay, but I want to stress that, the outputs doesn't just have to be 2 or 3 classes. It can, in fact, be a whole image, just like you're doing with your mini project. All right, so how do we, the first things that we do when we measure performance metrics to determine how well our model performs is we want to divide our data set into train and test set. You can do usually train, validation, and test set, although for the most part, I only do train and test divisions, right? So what's important here is that you train only on the train set, and then once the model's trained, you apply it to the test set, right? And that's basically, yeah.
And the reason why we have validation tests is so we don't overfit the.
Validation is sometimes used like when you have a model, you train it, and then you still want to do something else with it. It's kind of still training, and you're doing it on the validation, but the test set is the thing that the model should never see.
And the test is like a one-time thing, and once you use it, you need more test data, basically, right?
Well, I mean, you can use the model on the test set. The key is don't train the model on the test set.
Right.
The model should never look at the test set, right? You have to keep it a secret, if you will.
And then
Because
that's-
otherwise that's cheating. Then yeah, you can expect it to be really good. It's seen it. You know what I mean?
And the error, like the correlation coefficient being reported will be one from the test set, not from the.
Well, and that's a good question, actually. So we will see that as we do training, we print, actually, you can print the performance on the train set. It's just another piece of information. But really, the one that matters is the one on the test set. Like the one that would matter on a competition is the one on the test set. You see that? All right, so basically this is the graph of dividing the data like that. There's basically two approaches to this. The one that we've been using, that we will be using the neural nets, is because it's the easiest to do, right? It's just to split the data set into something like 80% for training, 20% for testing. However, you guys have also probably in your Weka project, you use tenfold cross-validation, right? And what tenfold cross-validation is basically taking the data set, randomize it. Let's say you're going to do this 10 times. So each iteration, you first take the whole data set, randomize it in some way. After that, split it into 10 bins. And then after you split it into 10 bins, you can grab, let's say, the first 9. It doesn't matter because it's been randomized. Grab the first 9 and you train the model on those 9. And then the 10th one you leave and you test it on it. And that gives you an accuracy or a precision or whatever it is. Yeah.
And it's doing that once, or is it doing 10 times?
You're going to do it 10 times.
Okay, so it's randomizing 10 times.
Yes, that's the
splitting
key.
it Into 10.
Yeah, I was going to say all that, but yeah,
Okay.
you can go ahead and say it. Yeah, you're right. No, you're right. Yeah. So that's exactly what tenfold cross-validation is. It's a for loop of 10 times. You grab the data set, first iteration, randomize it, split it into 10 bins, grab the first 9 for training, leave 1 for testing, evaluate on that test set. Boom, you get, let's say, 1 accuracy. Second iteration, what do? Grab the data set again, randomize. Split it into 10 bins, grab the first 9 for training, the last 1 for testing, got a new accuracy. You see that now? This is better because, you know, you'd never know when you're training a model. What if all you do in the 80% split here is that you got all the pictures of cats and you didn't get a picture of a bird? What are you going to do when you actually see a bird in the test set? You see that? And so this is the idea with tenfold cross-validation. You basically take your model to like you're more sure of the score that you're getting when you do tenfold cross-validation. Do you guys see that? Does that make sense? All right, this is harder to implement in code. You have to use libraries and things like that. What I say is just use the poor person's tenfold cross-validation, which is just changing that seed. The random seed, I always change it. Since usually when you're developing a program, you're running it multiple times anyway, because you're trying different things. By randomizing that, it's like you're doing a poor person's tenfold cross-validation. Although you can implement this in code, it makes the code a little bit harder to see, okay? All right, so now we're gonna get into these metrics. These are the ones that I'm gonna talk about today, which is classification. A lot of, as I said, this sequence that we're starting right now ends with CIFAR 10, okay? And CIFAR 10 is an image data set in color, all right? It's gonna require the use of the GPU for you guys to train it, right? So you guys already tried to log in and all of that. And at some point I will demo that again, how to play with Scholar GPU. It works really well actually for homework or projects. Okay, so we'll be towards the end, I don't know, sometime around the second exam, we'll have the CIFAR 10 competition. And you guys are gonna try whatever you can to win, All right, that's the goal to get. And how are you going to know that you won? Because you're going to be on the test set reporting your precision, recall, F measure, and so on. Okay, and whoever gets the highest with, because what I'm going to show you for this third of the semester is a whole bunch of techniques, right? But there is no recipe for how to use them. So you're going to have to mix it up and try this and that to see if you can get the best results. Yeah.
What is the ROC curve?
It's one of the metrics that we're not gonna use for this, but it's a metric that compares two things, and you look, it's, you know, like the curve moves like this, and it kind of determines how good it is or bad.
Gotcha.
But it's not one of the metrics that I use a lot. So
It's accuracy, precision, recall.
the metrics that we're gonna look at, ROC curve is like, this is a family. Accuracy, precision, recall, F measure, and confusion matrix are all a family. They're all related. So this is what we're going to cover. The ROC curve is another metric that's available that I don't usually use.
Gotcha.
And so it's something we can explore, but you know, it's not really my, you don't see it in that many papers all the time, but these you do, and you have to understand how they work. So let's start with that. Now, one important thing that I should say is, in the data sets that you have, like academic data sets, right? They're IRIS, MNIST, which we will use MNIST this semester, this sequence, and CIFAR 10. They are balanced data sets. What that means is that, you know, you have cats, dogs, and birds, and you have 50 of one, 50 of the other, 50 of the other. That's a balanced data set. When you have balanced data set, pretty much these metrics are all the same. If you have 80 accuracy, you have about 80 precision, 80 F mesh, and so on. Do you see that? Really, when these become important is when you have imbalanced data sets. And that's like, for instance, the classic case of fraud detection in a bank. So in a bank, right, if you're trying to do fraud detection, the majority of the transactions, hopefully, are not fraud, right? They're just like regular, normal transactions. 98% probably are normal transactions. And then 2% or less, way less probably, are going to be fraud. So that is a highly imbalanced data set where it becomes really important to look at all these metrics because these can tell you other things about your results. Does that make sense? All right, so that's what we're going to see now in the next example. Oops. Right. Oh, there we go. All right, so as you know, I've already given you this function. I gave this function, I believe, last week, probably, or sometime. We'll be using that function throughout the rest of the semester. We're going to use basically from sklearn, the module metrics, which gives us the confusion matrix and all those to get those values, basically. So you already know that. Right, these are the names of those modules as you import them from sklearn. All right, so here we go. So this is of these slides. I'm only going to do this first part. I'm going to let you think about it a little bit, and then we're going to do a use case with terrorism detection next week. You can read through it, it's there. All right, so let's keep it simple here. So what is this? That table is actually the confusion matrix for two classes, basically, right? So we're comparing here the true one to the predicted one, and the true one to the predicted zero. And then also we have the true zero and the predicted one, true zero, and predicted zero. All right, so basically what this tells us is that all those metrics, accuracy, precision, recall, F measure, are in relation to the confusion matrix, okay? Which is, and you guys know how to print that out, okay? So what is the accuracy? If you look at it, given this table, we can calculate accuracy as such. So the equations are given in terms of these letters. So out of all, which is A, B, C, D, right? How many were correct? So the correct are A and D. Why? Because it was a true one and it was predicted as a one. And it was a true zero and it was predicted as a zero. Do you see that? So that's basically what's accurate. If it was a true zero and it was predicted as a one, then it's incorrect, right? You may have seen this in your stats course as false positives, false negatives. I'll change the language of that in the second example. So to the more familiar for you probably, but I think this is more intuitive to understand. So that's accuracy right there. Very simple. Any questions? All right, so let's look at the next one then. So what is precision then? Precision is another metric that looks at this a little bit differently. Here it's gonna say precision only cares about A plus C. So it really just cares about these here. What are those? The predicted. So it doesn't care about all the examples in the world, right? It only cares of what my model predicted, how many were correct. You're missing out possibly a lot of things that you wanted to get. But maybe sometimes precision is what you want. Right? You don't need to find all the cases in the world. You just need that the ones that it finds are very accurate. Do you see what I'm saying, guys? So that's basically precision, right? So A and C, out of the predicted, how many were correct? Does that make sense? In another scenario, you've got recall. And as I said, in the second example, we're going to think about the terrorism detection problem, which is a highly imbalanced data set because out of 300 million or so travelers in US airports, right, only like 20 were terrorists, you know, or something like that. All right, so anyway, so now we have recall basically. And for recall, we can see it's A and B that we care about. That's the denominator. And what is A and B? The true. So out of all the things that we want to find, right, how many were we correct? Out of all of the real, you know, we don't want to miss anything here, right? So out of all, how many did we get? You guys see that? So out of cancer cases, how many does our model detect? We don't want to miss even one cancer case. You see that? Because that means that somebody would, you know, could die. So that's how you think about these problems, okay? So recall gives you that other, so remember, precision is out of the predicted, what the model predicts, and that's all I care about, even though it's missing a few, but its precision is pretty good. Or how good is it really at finding all of them, right? Out of all the ones, how many does it get correct? So A and B is the denominator, and then A is the, does that make sense? And then what is F measure then? So now that you've seen precision and recall, you know that you have to think about your task. Do I want, you know, you're building an application, right? Maybe for the healthcare field or something. So in the healthcare field, maybe you want high. All right, so plugged in, right? Okay. All right, we're good. All right, and then so you have to think of your application. Do you want, actually, when I almost think this way. I never look at accuracy. I know you guys saw it in WECA as the top one or whatever, but I almost, and nobody really, if you look at the papers, accuracy is not really the one that people look at because usually real data sets are not balanced. They're in fact highly imbalanced, right? So that's something to consider. But depending on your task, like I was saying in the medical field, maybe what your goal is to have high recall, okay? But maybe an administrator in a hospital wants high precision. Why? Because they don't want to pay for things that were unnecessary. You see that? So you have those two cases. However, a nice metric is the F measure, F1 measure, sometimes called also, which is a metric that combines precision and recall into one. So that's like the best metric because that considers recall and precision, is like it finds an optimal balance of the two. Do you see that intuitively? So it's like, I don't just want high precision or recall, I want one that maximizes both of them. And that's your F1 measure. So that's why you will see in a lot of publications or competitions that F measure is reported basically as the metric. So you can see this is just an equation. that combines what's important here to note. We'll dig into this function a little bit more when we do the second version of this. But basically, what's important to note now is that it combines both precision and recall, basically. Any questions, guys? All right, so hopefully those ideas are good enough for you to get started. I know these topics can get a little bit complex. So, so before we move on, there's the confusion matrix already. You've used this, and that's where those values come from. So remember, the goal is for the diagonal to have all the values, and then it shows the misclassifications, basically, right? All right, so round 2, as I call it, is the second version of this with a use case. So what I suggest is read through this, and then next week we will go over it, okay? But basically the scenario is, would you believe someone who claimed to create a model to identify terrorists trying to board flights with greater than 99% accuracy? So what if they told you this? Would you buy their product, right? So we're going to dissect this, into all the details to see if accuracy is actually a good indicator of the performance of this model, okay? Read through this one, and then we'll go over it on Tuesday again. But it's basically, as you will see, it's basically going at precision, recall, F measure, and thinking about how they work, okay? Any questions? Very important that you look at these to understand these ideas. And as I said, I'll come back to it on next week. All right, so I've covered this topic, and now we're going to officially, finally, get into neural networks. So it's this link here. All right, so I have, there's various things that I'm going to do today. In particular, I'm going to do these 2 Python scripts. We're going to go over them. They may use PyTorch, I think. So this might be your first introduction into the PyTorch library. So what is PyTorch? It's like NumPy. So you already know NumPy. You're already familiar with NumPy. PyTorch is like NumPy, only that it allows you now to create very powerful deep neural networks. You could build the code for ChatGPT, the model that was trained was done in PyTorch or TensorFlow, one of the two. All right, so this is like state of the art as far as library. This is not a toy. This is like a real thing, and it'll run on the GPU and everything, as we will see later. All right, so let's start with these. Have a PDF here, so I'll go over these notes. This will kind of end. I like to start this sequence with history on this. All right, so these slides, the last slide is basically the history of neural networks from like the 1940s, right? So we'll start there, but first I'll give you some ideas. All right, so I call this usually light neural networks and history. It's just basically a very simple introduction into some of these basic ideas. If you notice, I've got my X and Y there yet again, right? So that doesn't go. Those fundamental things about the pipeline do not go away. Everything that you've learned so far, still there. The only thing that I'm gonna plug out is K and N, right? So I'm removing K and N, and I'm gonna insert now neural networks. You already did this in the WECA assignment, right? You ran neural networks, in fact, in the WECA assignment. Do you know which one of the algorithms was the neural network? No. Huh? Nope. That's the decision tree. Yeah.
Neural networks deal with derivatives, not numbers, right?
Somebody said something? Multi-layer perceptron. Yes. All right, that sounds confusing to you now, but by the end of this sequence, the goal is you will understand why it's called a multi-layer perceptron. It actually comes from a perceptron, which was the first thing invented at Bell Labs in the 1940s, right? So that's the first idea. That'll be actually one of the first algorithms that we will take a look at, okay? All right. So let's kind of start at machine learning, right? And machine learning is divided basically into several areas. It used to be that I could just say machine learning is 2 areas. I used to say that a lot. And now it's like, yeah, it's like 3, but maybe there's 2 more. It's like there's all these classifications going on. Nowadays, is it a generative model, which is kind of what you guys are doing? Or is it a classifier? So there's also that as well, right? Generative models are basic. This is why I want you to do the KNN so that you understand, or I'm doing a generative model. But anyway, machine learning in the past was divided into, you can see here, SL, UL, and RL. Those are some classifications. That means supervised learning or unsupervised learning. And RL means reinforcement learning, right? So those are definitely 3 topics that we will cover in the class. Although I should stress that the majority of the content will revolve around supervised learning, okay? But I will cover unsupervised and RL actually in that third of the class at the very end, the miscellaneous. Nowadays, you have also this idea of semi-supervised. And semi-supervised is basically, it all relates to data, right? So it's data that it's kind of like annotated, but not annotated by somebody that you hired to annotate. It's just annotated because of how it is. For instance, just a book in English. The cat is sleeping. That sentence exists in the book, right? Somebody wrote it. And that's, in a sense, annotation because you know that the cat is sleeping. Sleeping comes after is, and is comes after cat. You see, that structure can be used nowadays to train machine learning algorithms. So that's an example of semi-supervised. But anyway, in general, you're going to have supervised learning and unsupervised learning. So some examples of supervised learning are KNN, which hopefully you can ground yourself in KNN and know what that is. Naive Bayes, which is another classifier that we looked at, and then this one, NN, which is the subject of the topic these few weeks, next few weeks, is neural networks. Neural networks have a lot of names like artificial neural networks or deep learning, right? So all that is really the same thing, right? Just scaled up more and more. And so actually what's really nice about this sequence is that it's very nice. You start with one thing and then you like add something and it becomes like the next level. And then you add more and it's a multi-layer perceptron. And then you add more to that previous and it's deep learning. You see, so it's very incremental. So make sure you don't fall behind in a concept because then it's going to affect your understanding of the next ones, okay? Now you already know one thing probably from your stats class, which is linear regression, right? We're actually going to start. Those are the 2 fundamental things, the perceptron and linear regression, which linear regression is like a neural network, believe it or not. All right, so here I wrote other things like singular value decomposition or KNN, oh, sorry, K-means, which is the version of KNN for unsupervised. So what is the difference basically between supervised and unsupervised learning? It's really right here. So remember how in the work problems I said X and Y, right? So we're correlating the X row to the Y row, right? And that's basically, it meant that we had the data representation of something and the label. So we had an image of a 7, and then we had the label 7. An image of a 3 and the label 3. Do you guys see that? Is that clear for everyone? So that's supervised learning. So what is unsupervised learning then? Unsupervised learning is simply the X without a Y. Yeah. And
Very stupid question. If there's no labels, vector,
yeah.
like,
How does it learn, right?
how does it learn what you're learning for? I guess.
Because you can learn, we'll see this algorithm. So you, yeah, no, yeah. So no, it's a good question. So usually in supervised learning, we learn to correlate the X's and the Y's. But what if you don't have the Y's? Then in that case, you cannot use KNN or neural nets in how we're gonna, use them for supervised learning. However, there's another set of algorithms that we can use. You see what I'm saying? There's basically other techniques. So I'll give you an example. We have a vector space of cats and dogs, right? So we know these were labeled as cats, these were labeled as dogs. A human did that. In an unsupervised environment, we still have data. So what we could do is create two clusters and just say, group the things that are similar to each other. What are they? We don't know. But can you group things that are close to each other? Sure. It's another distance metric, right? I grab two centroid points and then just compare the things around them, right?
And
And
you just call it label A, B, and C. And then
you
like later on.
you just say, if you say two, then A and B. You could say I want three clusters, so then A, B, C. But the key thing is, what are those things? We don't know. As it turns out, though, sometimes that can be useful. You see that? So we'll see that later in the semester, so don't even worry about that. But I just want to stress that if you don't have labels, you can still do a lot, okay? Things like, for instance, the ChatGPT was pre-trained without labels, but it was trained on language. So it basically learned to understand that if I see this sentence, there's a sentence that follows it. So it learned to correlate like words that were next to each other or sentences that were next to each other. So that's why it's called semi-supervised. Although no one annotated it, there is structure there just in the fact that humans write in a specific way, not randomly. Yeah, please.
Can you change it in the future?
The way.
ChatGPT,
What?
like instead of reading sentences, it's using the same. Whatever.
Oh yeah, so ChatGPT, you think of it as this way. It trains on an unsupervised, and then it trains in a supervised. But the thing is, it needs a lot of data to learn. So humans can only annotate this one. This is called fine-tuning, which basically means it's a step where you can only grab like 100,000 pairs of sentences and you label them. So, but that's not enough to train a ChatGPT. Before, you need to training it in an unsupervised way because you need to give it tons of data. So what's the trick that they did? They just figured out, if I grab a sentence, the cat is, then the cat is sleeping. So it just guesses the next word. And you can do that from any book, because go to a book, grab a sentence, right? Put it in as an input, and then put it in as an output, but shift it. Remember the shift example that I gave you guys at the very beginning of the semester with NumPy? That's what it's for. You're shifting it so that here it sees the cat is, and here it's going to see cat is sleeping. And it only learns to predict that last word. Do you see that? That's it. This is literally how it does this part. Because you can do that with all the websites, all the books in the world, everything, right? Where you can grab a sentence as input and output, but just shift it a little bit. And that's how it learned. Astonishing. So it learns in a sort of, and that's called semi-supervised. There is structure, but it's just structure of text, basically. Any questions, guys? So anyway, we're not building ChatGPT in this class. I can tell you that right now. But we are gonna try.
Totally like old data set.
You can't. Literally, it's impossible. You need 10,000 GPUs and all the text in the world to do this part and be as good as GPT-4 or Llama or now Gemma from Google. So there's 3 contenders. Okay, but you guys can totally do the fine tuning once you have a Llama or something. But anyway, that's too far into it. Let's start at the very basics, okay? So unsupervised, no labels. Supervised, labels. You're a little bit familiar with this, and this is what we will be focusing on, okay? So image of a cat, label cat, image of a dog, label dog. All right, so basically here you can think of a neural network kind of as this, right? So think of it as you have an eye, and the eye basically just sees a picture of a cat or a dog, and it's going to be connected to a whole bunch of points like roads, like cities. Imagine there's a whole bunch of cities with a whole bunch of roads connecting them, right? The key question is, which roads to which cities should you select to get to the final destination. That's kind of a good analogy of neural networks, right? You have basically an input and you're going to have an output, which is what you're trying to predict, okay? So we've learned a few techniques about this. So for instance, we know that we can take an image that is 28 by 28, spaghettify it, right? And then that becomes the input to our box, which is the neural network. And then we just predict the Y, right? So this should be very familiar to you. We're going to still have X inputs, Y outputs, but this structure is what we need to focus on today. So yeah, go ahead.
What's the
Artificial neural networks. A lot of people will start with a picture of a neuron, like from the brain and stuff like that. I usually don't like to view it that way because I don't think it's like biological. It's more like math, but we're gonna do some of this very basic stuff today, okay? So anyway, here is a neural network more worked out, okay? If you look here, there's a few interesting ideas, all right, and some terminology. So usually neural networks are drawn in this way, okay? So, and they go in that direction. So like that. Starts here and it ends like that. So if you notice here, this is going to be the input and this is going to be the output, okay? So the input here is what? 784. What does that tell you automatically? It's an image, 28 by 28, that I've spaghettified, right? That's the first thing. We've talked about that a lot. Notice the features are X1, X3, X7, all the way to X784. What are they exactly? The values that go in here? They're pixels, right? So they're basically pixel values from the image. Everyone with me on that one? They're pixel values. And the label is over here. In this case, the neural network predicts either a cat or a dog, okay? But we use this idea called one-hot encoding, right? So we'll cover all of this in more detail later. And one-hot encoding basically means if we have two classes, we have two neurons. So this is the output layer, and we have one neuron and another neuron. So if it's a cat, this value is 1, 0, right? And if it's if it's a dog, it's 1, 0. If it's a cat, it's 0, 1. You see that? So basically, this neuron is always to say if it's a cat, and this neuron is always to say if it's a dog. In between, if you notice, I have these things called hidden layers, okay? Hidden layers. And they're basically, as I said, if you think of the analogy that I gave, you start here and you want to get here. These round things are cities, and then you have these roads. The question is, which roads do you take to get to your final destination? And keep in mind one thing, that you have like multiple cars leaving, right? So every neuron has a little car, right? And they get to a destination and they kind of like share information, and then they decide on what different direction they want to take. You see that? So at the end of the day, you have this idea, right? That you set up an input layer, however many hidden layers you want, and basically you need to connect them, all right? You want to connect them from, let's say, from this first neuron X to this one, and then from here to the next one, and then from the next one, and so on until you get to the final label. Do you guys see that? So that's the terminology here, okay? So input layer, hidden layer 1, hidden layer 2, hidden layer 3, output layer. The connections have a name also, and it's weights, okay? So these are going to be the weights, and you can see the arrow there. The circles in here are called neurons, and this is the thing that is defined by you guys. You can define, for instance, that I want this hidden layer to have 50 neurons, okay, or 60 neurons. Okay, so that's basically some of the terminology. Also, this is called architecture. So basically, you'll hear this a lot, or you'll read about this a lot, defining the architecture of the neural network. So I've shown you a picture, right? There's two other representations of this. The function representation of the neural network, the matrix multiplication representation of the neural network. So there's like 3 ways of viewing at this. So this is a neural network, and it's in fact a deep neural network. Why is it deep? I'll tell you the names right now. So if you only had an input layer connected to the final output layer for classification, that would be called logistic regression. So it's like linear regression, but for classification. Okay, so that's what that means. So what is the multi-layer perceptron? The multi-layer perceptron that you guys used in Weka is one input layer, one output layer, and one hidden layer. That's a multi-layer perceptron. So then what is the definition of deep learning? Deep learning is more layers than just one hidden layer. So for instance, if I do an input layer, an output layer, this layer, MLP, I add a second layer, that's deep learning. That's all deep learning is you're just adding more layers and more connections to the model. Does that make sense? All right, so right now, as I said, this is one great thing about this is we're going to be repeating this a lot of time, for a few weeks. But for now, I just want to stress a little bit of the terminology. Yeah, go ahead, please.
This example,
Yeah.
Wouldn't this be a learning then?
This is deep learning, yeah. So if I meant to say that, you're looking at a deep learning architecture. Quite simply because it's got more than one hidden layer. Yeah, please.
What do the layers even do? Like,
They're just calculations of numbers. So we're actually going to see this. If this is a matrix multiplication, so you have this x1 times w1, and that becomes a value that goes in here.
Yeah, why do I want to do it 3 times? Why would I want to do it 3 times?
Why would you want to do it like, you mean
Right
like here to here, and then from here to here, and then from here to here? Is that what you mean?
The end layer.
Yeah, why would you want to do that? That's a good question. So I have an analogy for that might be helpful. Let's say that you're looking at this image of a cat, right? So in the first neuron, these two are inputs, pixels basically in the image, right? And it's maybe like a little thing and another little thing, 2 straight lines, but kind of like this that always appear together. Do you see that? It might be that it looks at this one and that one, and one is like this and the other one is like this, and they always appear together. So this neuron starts to connect those two things as a thing, as it's looking at tons of images. Let's say that it looks at 1,000 images, and out of those 800 times it saw this and this together. So that neuron starts to become like, hey, when I see those two things together, I'm going to become a number like 1.
It's the weights.
It's the weights. So the weights have to, yeah, the weights say, I'm going to pay attention to this pixel. So there's a pixel here and there's another pixel. Let's say they're like that. So when I see them a lot when I'm looking at cats, for instance, or dogs, right? And so now the weights are going to become high for that to kind of activate it as a, it fires up. I'm seeing this. So now this neuron here becomes a neuron of detecting this. Do you see that? And, yeah, go ahead.
Why are you saying we can pick the amount of neurons?
You can, yeah.
What's the reason for the nodes?
It's more flexible. So let me use another example, right? So I use this, right? I use this. Now on this, let's focus in on this one here. You see this neuron? Or actually, yeah, this, I only have one connection here, but imagine there's 2 connections from over here, from 2 pixels, right? But now it's this one and this one. Those 2, it sees together and it learns that, in images of cats, I always see this one and this one. I'm going to like connect those 2 things together. So now this one fires. You see that? And now the neural network then, as it's doing a lot, because the neural network, it tries a lot of things, right? It tries other connections and it doesn't do well. But when it sees this pixel and this pixel, fires this neuron. And when it sees this pixel and this pixel, fires this neuron. And now it's going to try to say, well, if I see this and I see this and I see this and I see this, It's almost like a circle, right? I'm starting to fill in like a circle there. And so this neuron actually pays attention to the bottom ones and the top ones. And boom, it starts to fire to say, you know what? I'm seeing this weird shape of this, and that's a circle. Do you see that? And so now this one fired here. And so now what could that be? A circle? Maybe it's an eye. So it's starting to find cats or dogs because they have an eye there, right? And so it fires, and then maybe there's another one that has to do with fur, which did the exact same thing. Let's imagine that's this one, okay? So now you have, I see fur, I see this circle thing. I'm going to connect those two things. And so now it fires this one. And it just so happens that whenever it makes those connections, it predicts cat, and the prediction is always right. The algorithm does the heavy lifting. This is the one key thing that should frighten you for real about neural networks, that you can give them stuff and they will figure it out. So it's not that AI is going to kill us all, right? That's not really the fear that Terminator is going to come in and extinguish humanity, but it's the thing that honestly, you can give it. I think they gave it chess, for instance, right? They gave it chess, and chess was beaten like 20 years ago. But then they let deep neural networks play chess. And what they did is, you know how there's masters in chess like Magnus Carlsen and, I mean, amazing players. But they can't beat deep learning. You know this, right? Magnus Carlsen, the best human in chess, cannot defeat neural network. And when they studied the neural network and what it did, it came up with new moves. Like new Queen's Gambit or whatever that is, its own things. And also, like, it would kill like 3 very important pieces and still win the game, which is something humans would not do. We have our own boundaries, right, of how we behave, and the algorithms does not, because they can just do this. Remember, as you will get very used to this, you will do 10,000 iterations of this. Remember that it's not just randomly changing weights, it's intelligently changing the weights, because it uses a set of algorithms called feed forward and back propagation and stochastic gradient descent. There's 3 of them, and created by Jeffrey Hinton and people that are very famous. And so just give me a sec. So instead, you could try out randomly all the weights in the world, right? You can imagine that. But unless you have a quantum computer or something like that, it would never finish, right? So we can't do that. Instead, we have to intelligently change weights. So like, we're at this set of weights, and then do we change these weights by adding a little bit or decreasing a little bit of the weights? You know what I mean? And there's an algorithm for that we will cover later, not today, but we'll cover it. Does that make sense? So what's important is, your question is really good. And this is kind of what I was saying, is that at the end of the day, this is for supervised learning. You got an input, and you know that what you want to do is predict cats and dogs, right? So then it starts to just try, okay, if I, these 2 pixels randomly, I put them together, predict the next one, another 2 pixels, put them together, then join those. I predict cat, but it was a dog. Didn't work. I'm going to try another one, this pixel and that pixel, join them together, this cat, it was a dog. Didn't work. But there's one iteration where it picked, as I was saying, this one and this one, which actually, if you looked at it, it was this and this. And then it picked these 2, and it was like this and this. And when it took these 2, you got the round shape, and then, you start building things, and it predicted cat, and it was a cat. That's really the key to understand, is that it tries a whole bunch of things, predicts, compares to the real. If it's accurate, those are good weights. If not, it just keeps trying weights until it finds the correct set of weights, but it does it intelligent. Make sense? Now, so to ask your question, what if I had just done 1 layer? What's the problem with that? It found this and this, and in another one, it found that and that. But because I did not give it the 2nd layer, it never could make the connection that this and that went together. You see what I'm saying? It wasn't able to discern that because it was missing a layer. So then what does that kind of intuitively tell you? Deeper is better. Yeah,
I
please.
was gonna say that, like,
Yeah.
the amount of hidden layers, what is that determined by? I think you just answered.
Yeah, I think so. Yeah, it's and that's intuitively and also like empirically. ResNet, which probably you need to use to win Sci-Fi 10, has like 128 layers. Yeah, and
First your question, but the
Go ahead.
stochastic gradient descents.
yeah, what are the
Is that just
algorithms?
like a gradient descent, but one more term thing, stochastic process. or-
Stochastic just means random, so there's some randomness in there, but the algorithm is deterministic. And what you're trying to do is you'll see you're trying to figure out how to adjust the weights. That's the key thing. It's like, think of it this way. Right now, quantum computer, just give it in parallel all the possible combinations of weights in the world. As you know, that is a huge number that you would never be able to process. Right? So what you want to do is you want a way of changing those weights intelligently. Okay? And that's what those algorithms are for. All right? There's only one set of algorithms, by the way, for all of AI. It's not like there's 10. There's 10 classifiers, KNN, naive Bayes, but there's only one set of algorithms to train neural networks. Okay? Any questions? Yes, sir.
This seems way more like thorough and in-depth than the KNN.
Okay. Putting down KNN.
I mean, like.
I'm just kidding. Go ahead.
Looks like so intelligent.
Yeah. Why did we use KNN? Why did I waste your time on KNN? It's because we got to start somewhere, and this is by the time you get to understand this, it takes a while. KNN, you guys already know.
I mean, like if I was a machine learner and I had to pick.
Why would you ever use KNN?
Versus, yeah, not like-
I used a KNN recently to solve a problem. You don't always need a bazooka. Sometimes you can just hit it with this thing, and you know what? It'll work. Data is king in machine learning always.
And it depends on the problem, right?
It depends on the problem. Like that thing for Gary Works, it was just a KNN, and it's just like they were happy. Yeah, there's neural networks in there, sure. You know what I mean? And you don't always need. That's kind of the important thing. Also, I should say this. XGBoost. I give this example because it kind of like changed my way of thinking. It's a decision tree. You guys have used decision trees, random forests. XGBoost is just like an extreme, it literally means extreme, right? So it's an extreme tree. Sometimes that's more than enough. Neural networks nowadays are for like really complex problems. Like if you're dealing with really complex images or language or, it's almost like there's a lot of things you can still solve with KNN or decision trees are actually very powerful. Okay? But yeah, you're right. I mean, this is powerful, and you can build. You'll see very quickly. You'll be able to build a deep learning algorithm. It's not difficult, right? Difficult. It's actually trivial to do. But you need this whole class is called machine learning foundations, right? So you're supposed to understand how it works. Okay? But you'll be building probably by next Thursday, or we'll try to build a neural network that we can deploy with Python. Right? Making sense? Any more questions about this? Yeah. So going to conclude this slide, the number of hidden layers, you can set as many layers as you want. You don't always need to do 128 layers. Keep in mind, though, the bigger your image is, the deeper your network is, the more computational power you need. This is why we need GPUs, right? And MNIST, you'll be able to run on your laptops probably. Sci-Fi, you will not be able to run on your laptops, okay? So just keep that in mind. All right, so let's move on. And then, yeah, the number of neurons, that's actually kind of you're the architect. You figure it out. It's kind of a bit of a trial and error, although there are some rules of thumb, like especially with images, if they're really big, do a funnel approach. What a funnel approach basically means is if this is 200 neurons, then make this one 100, this one 50. Why? you're forcing, if you give the neural net too much space, it'll think too much. Force it to think with less every time. That's kind of a rule of thumb, but in I mean, at the end of the day, it's not, you got to experiment. All right. All right. So let's move on to the next slide. Here they are, for those of you that really need to know these. The frameworks obviously are TensorFlow or PyTorch. For the most part, I'll be using PyTorch. This is really what a lot of people are using nowadays. TensorFlow was the very first one to come out, but they use Google, so Google always like makes everything too complicated.
Sure.
Yeah, too complicated. And so PyTorch kind of ate their lunch in that sense. They're more focused. So it's really like currently it's well respected. The algorithms are feed-forward algorithm, backpropagation algorithm, and gradient descent. I will give you some papers to read, mostly the classical papers, just to kind of be informed. To give it a little bit, and I'll finish with history today, so I'll go over. Okay. But basically to figure out the weights, that's the essence. Today we'll do like one of the two parts of this duality of neural networks, if time permits, or this week, I should say, Thursday when we do the coding exercise. Vector space model, remember that? That's still here, right? And so you're still going to think about that just in the context of neural networks. As you can see, I wrote C, C++, CUDA, and GPUs. So GPUs are essential for all of this, right? You guys are using Google Purdue Scholar. Basically, GPUs, there's like two contenders right now, at least, AMD and NVIDIA. NVIDIA is the dominant organization. They built a proprietary library called CUDA in C, C++. So PyTorch just is Python, but the libraries are compiled in CUDA, C, C++. But we never have to write in those languages. We just write in Python. You've already done this with NumPy. It's a very similar approach. All right. So here is kind of the idea of the neural network. Here's an example kind of the question you guys have. So these are weights, right? That's kind of how I defined it. So we got the input. Okay, so let me ask you this. What is this neural network? What name does it have? Yeah, multi-layer perceptron. Very good. Why? It's got one input, one output, and one hidden layer. Okay. I haven't mentioned anything about activation functions yet. That's part is missing, but don't worry about it. Okay, so there's just a little bit more. So yeah, very good. Multi-layer perceptron has one hidden layer. So remember, you got the X's, the W's, and that predicts H1, right? And then H1 and these W's predict the O. Do you see that? So basically, you can write, remember I said neural networks can be expressed in several ways. This would be like expressing it as functions or equations. So what do I have here? This one, input is X1 times W1, which are these two things, right? So in this case, I have literally X1 times W1 plus X2 times W2. Do you guys see that in a very simple way? What is X1 and X2? Your two inputs. You know, it's 80 degrees in here and, you know, in February or something, right? Those are the two inputs right there. What are you trying to predict? Should I drink some water or not? Something like that, right? So then you have X1, X2, but these W1 and W2, you don't know them. Okay, you have to learn them. That's what neural networks do. They have to learn these W's. But if you look, X1 times W1 plus X2 times W2 gives you what? This one. You see that? And then H1 times, yeah, I put H1N1, but this one. So H1 is the hidden layer, and then N1 is the neuron itself. So H1N1 times this W, the purple one, gives you what? Oh, do you see that? That's the relationship that you have there, which is what we're going to be This is how you express the neural networks as equations. Yes, do you have a question? Oh, does anyone have a question? Do you guys understand this idea? Yes, sir.
Does it say what the output form was?
It should be predicting in this case, whatever these, just if you look at this output layer, it has 2 neurons. So that tells me it's predicting one of 2 classes, one of 2 things.
Right, for the W1, W2.
Mhm. Oh, you want to know the values? What those values are? Sure, you can see those. Oh yeah, you can see those values. No problem. You can totally see the weights. In fact, you'll see that what we do is you define a model and then you call it model.parameters. And the parameters are these values here, the weights. And you can always inspect them if you want during training. But what you want is you want to run 1,000 iterations. And at the end of 1,000 iterations, you want to arrive at the set of weights that is the optimal for your problem. Any other questions? So again, I'll repeat, this is a very simple way of looking at the neural network as equations, right? So we have x1, x2, so x1 times w1 right there. x2 times w2 right there. So this is called a linear sum, right? So these are linear models so far. This is only a linear model because it's missing the nonlinear part, let's call it that. And I haven't added that, but I will show you later. Okay. So yeah, and then once you get to these, it's like these H1s become the X here. They just like become the input to the next one. So now you start from these H1N1 times the W's here that also need to be learned, and you predict the next one. That's why it's called feed forward and back propagation. So it's propagating one layer at a time, or it's feeding forward one layer at a time. So you start here, you run it to the next one, and then these outputs, you run them to the next one, and so on. When you predict something, let's say that you predicted here a 1, and it was, so this is the predicted is a 1, and it's actually a 1. What does that mean? It was a correct prediction, right? Yes. So that means that the error is 0. Now you need to use that little piece of information to propagate back. And you're going to go work your way back from this one with that information to this one and this one and update the weights. How that's done, that's the algorithm back propagation. We'll cover that later. That's literally Jeffrey Hinton's invention and their team. Okay. That's it. That's it. I mean, there's literally, after that is just like here, a little tweak here and there. The weights, how are the weights in a simple, intuitive way? How are they computed? You have a weight, let's say ij, right? Weight ij. So you start with weight ij plus or minus, just be consistent, something called the learning rate, which is going to be a little value that you set up, let's say 0.0003. So that learning rate is, you take the weight and you always are either adding or subtracting that from the weight. The question is, do you add it or do you subtract it? That's the question. Do you see that, guys? That's how you update the weights. You start with whatever the weight, it's like iterative, like a counter or an accumulator that you learn in programming, right? So you have the weight and you're trying to change it. So you're going to add or subtract a value always, like 0.003, which is called the learning rate. But the question is, where you are in the training, do you add that to the weights or do you subtract it? So you need to figure out a technique to determine if this should be a +1 or a -1. All of that, basically, the whole framework of PyTorch and TensorFlow is for that one little thing. Yeah, Henry.
So for the derivative or whatnot.
That's the derivative, yeah.
That's the derivative.
That's the
And
derivative.
it's just a matter of direction.
It's just a matter of direction. You said it very nicely, yes. So I have here diff. This diff that you see here, that's going to go to the derivative process. Whatever that returns is going to be a plus or a minus, which is really all I care about. And then that determines if I'm going to add or subtract from that weight. Obviously, a lot goes into that, but But the
Right.
but the way of updating the weights works like that. Getting this value, there's a lot involved. Okay. All right, good. So again, don't worry about, this is a few weeks of this, right? So, but right now I'm just going over some terms here. All right. Yeah, this is the feed forward direction. What you're doing is you're comparing the real to the predicted. So if you notice, we denote the real just by y real, and the other one is going to be y pred. So it's basically a function where x is the input, okay? If you notice here is y minus this squared. Why? Because whenever we take differences of things, sometimes the difference could be positive, sometimes could be negative. But we just want a magnitude of how different they are, so we square it. Okay? That's one of the loss functions that you've been asking so much about, actually. So we are starting to get there. One thing I want to say, in neural networks, there's two functions. The inference function and the loss function. Okay? Remember that. And it's like they're playing a game against each other. So remember it that way. Okay? For now, terminology, but I want to do the history part. So, okay. Oh, we'll learn that later. We got to drill down into all of these things that are like each one. Yeah, right. Yeah, these are like hour-long lectures. Okay. All right. So anyway, this is kind of the basic idea. This is kind of the idea that, but let's not even get to that yet. The backpropagation algorithm, you can Google it now if you want to start reading. The paper was Rummelhart, Jeffrey Hinton, and Williams, Nature, 1986. Nature Letters, I think it is. You can take a look at this paper. It's like, if you ever wonder what a seminal paper looks like, right? An amazing paper, that's it. All right. All right. So the last thing I want to cover today is the history. And kind of, giving it context is actually really important. Okay. So this is kind of the history of neural networks. Let me move this. All right. So basically, I'm not going to go to like Pythagoras and
Screen sharing. Or no,
Is it?
recording, or is that the recording, or is that?
Is it? I wasn't recording any of this.
No, right now you.
Oh, I just paused it. Oh. So we're good, right? Yeah. Do you want me to? Sorry, it says it's recording right there.
It was, I think it paused the sharing of the screen.
When I moved it, right?
Yeah.
All right, so we have about 15 minutes, so I kind of want to go over this today, just kind of give you the context of the history. And then obviously on Thursday, we'll get into code and we'll start playing with some of these ideas, okay? So basically, I'm not going to, obviously this builds on top of Pythagoras and all of those people going Euclidean distances. So that's thousands of years ago, right? But we're going to start in like modern neural networks. So basically the story would start around the 1940s, okay? Kind of in parallel, there's two big things. Claude Shannon, right? You guys know that, the father of information theory and basically the digital age. So Claude Shannon did cryptography, did a lot of the stuff that you guys learned for networking, but he did some things like entropy, cross entropy, define all of those. We use some of those concepts in machine learning for learning. He also was a very eccentric character who wrote a unicycle at Bell Labs, right? He was hired at Bell Labs just to have an office there and just kind of people have questions, keep your door open. He was a genius and invented a whole bunch of things. Anyway, he did a robot maze. So it's like a little mouse that would find the cheese. So he wrote an algorithm. A lot of AI stuff, but not really machine learning. Okay, except for the fundamental entropy and cross entropy things that are used for the actual training. We will see this idea. All right, there are two loss functions, mean squared error and cross entropy. And both of them we are going to look at in the course later. Mostly the story of neural networks starts in the 1940s at Bell Labs with Rosenblatt, and that's going to be with the first algorithm called the perceptron. So you can see how multi-layer perceptron comes from perceptron. All right, so this will be one of the first algorithms that we're going to look at, the perceptron and also linear regression together. Because if you look at them, they're simple and they allow you to build on top of them to understand more and more deep learning. Do you see that? After that, in the 1940s, you can look this up, and I think I have a picture of this in the GitHub. The perceptron was obviously like, they just invented the transistor. Like that was also invented in the 1940s at Bell Labs. So they weren't even using transistors at the time. Then you have Adeline. This is another algorithm. And then you can see between like the 50s and the 80s, silence, right? Not really that many developments, but people were still working in this field. Around this time in 1986, Jeffrey Hinton, Rummel, Hart, and Williams created backpropagation. That was the algorithm that they still use today. So you might ask then, if they had the algorithm in 1986, why didn't they have ChatGPT in 1986? What was missing? Yeah.
They roll backwards.
Huh? Think about it. You got to think about this. Data and what else? Processing power. Those two things were missing. Think about it. In 1980s, well, in the 40s, they had the perceptron. They were already talking about computers that were like humans in the 40s. There's an article. I'll show you later. But in 1986, Jeffrey Hinton and his team, they were already doing neural nets. They devised the algorithm that today is still in use, but no ChatGPT, because two things were missing: all the data that we need and the computing power. So we have to kind of wait for that. So really, it's a funny story that Jeffrey Hinton was basically, the anecdote is he and his team would go to conferences and they were put in like the worst table in the back. They were like the neural networks guys, but they were persistent. They loved what they were doing. Today, nobody laughs at them, right? So today, they're highly respected because they just did what they loved. All right, anyway, so that kind of takes us to the 2000s. Still, nothing has happened. The big event happened in 2007, which solved one of the two problems. What happened in 2007? NVIDIA released their GPU. Did they release it for AI? Nope. They released their GPU for what? Gamers. Gamers. But as it turns out, the operation that the GPU performs for gaming is the same operation that is performed for machine learning.
Graphics is just vector space.
Yeah, graphics. Exactly. This is a very good way of putting it. What is it? What is it? I don't know. You guys don't remember this because you're too young, but do you remember maybe in video games that like rendering of an image like this? You guys would not stand for that, right? Like starting at the top and then, but a CPU needs to do this, right? Why? Because it's got limited, it can't process all pixels at once. Do you guys see that? If you move a car or a person from here to here in a computer graphics environment, you want all pixels, the one in the feet and the head, to appear here instantly, right? A GPU does that because it does it in parallel. But a CPU needs to do this. Right? And you guys don't stand for that. So anyway, that was the thing that NVIDIA was trying to solve. As it turns out, that's the same thing as a matrix multiplication, right? You multiply X times weights to get a result. Or in the case of computer graphics, what do you multiply? X is what? The mesh. All the points in the game. And what do you multiply it times? A kind of a weights thing, but it's a weight of rotation and stretching. So basically what you're doing is you multiply this times the mesh to rotate it and move it somewhere else. Same idea. So anyway, in 2007, they released the GPU for video games, parallel hardware. This is built on top of CUDA, C, C++. There was no PyTorch or TensorFlow back then, just this. However, what happened was also during this time, let's say between 2007 and 2012, 2012 is the other key year. In 2012, every year they had a competition. It's called the ImageNet competition, where they had back then, which was almost impossible, 1.1 million images of things. That's CIFAR 10, right? 1.1 million images. And they had like 20 classes. I can't remember exactly. So the task was simple. You would go to this competition with whatever model, KNN, random forest, some neural net. People would support vector machines was the big thing back then. And they would train a model on the train set, go to the competition, apply their model to the test set, and then they would evaluate performance based on what? F measure. Whoever had the highest F measure would win. So every year they're in like the 70%. You understand this now, right? 70% F measure every year. In 2012, something called AlexNet went in there, which was a thing by Alex, I don't know, some Russian name, and Ilya Sutsketer, and they were students of Geoffrey Hinton, again, from the University of Toronto, entered this competition and won with something called convolutional neural networks. And they were basically a neural network, okay, that was trained on GPUs. This is the other thing also. They wrote the code like in C and the CUDA libraries to implement neural networks and backpropagation and won the competition. And where everyone was getting 70%, they got like 85 or something. It's a big margin. For anything in machine learning, that's something happened there. So that was the moment that Facebook, Google, Apple, like, they already had this need, but they had no clue. And this is where they noticed. Maybe they had heard a little bit about neural nets and GPUs, but they made it happen. Do you see that? You see how important that was? Because you had the algorithms first, then you had the computing power. And then in 2012, what happens? Facebook and Google find out about it. And what's that brings in that last component, the data. If you look, Geoffrey Hinton, Ilya Sutsketer in 2012, they were just looking at ImageNet. They're a university, they're academia. They don't have all likes and all that stuff that social media has. But once Google found out in 2012, they immediately, they got in, they bought actually, that guy Alex and Ilya, they created their own startup and they just bought it because they wanted to hire them. And that's how you do it in this field. So they hired them, they went in, to Google and stuff. The funny anecdote about Geoffrey Hinton is he's an older gentleman, a professor at University of Toronto. He said, I'm not moving to Silicon Valley. Thank you, but I'm not going to California. I'm staying in Toronto. So they just went to Toronto and built Google around it. So it's true. It's very true. It's very true. So that's why now Toronto is like the second or third Silicon Valley in North America. Anyway, so that takes us to 2015. It's been like 3 years and Google, Facebook already developed their frameworks. TensorFlow was first and then PyTorch. All right. And once that became available, then we can all write neural networks because before writing in CUDA and C is not easy. So if you want to do this at the C level, you can, and I encourage you to do it, but it's really hard. Whereas PyTorch and TensorFlow change everything. Okay,
Like an abstraction.
they're abstractions. They're literally like wrappers around things. So the libraries are in C because those libraries need to speak to the firmware of the GPU, which is CUDA for machine learning. And they built just like NumPy, PyTorch or TensorFlow. And they're basically libraries that we write with those libraries, but it's almost like they get compiled into C code, if you want to think of it. Do you guys see that? Yeah, Henry.
Keras is like a wrapper around.
Keras is a wrapper around. So this is so elaborate nowadays that TensorFlow has low-level API and high-level API, just like PyTorch has low-level API and high-level API. What that means is the more higher-level API you are at, the more abstraction there is. So there's like for, you know, students, professionals, children, toddlers, you know what I mean? So they're making it very, nowadays it's like you want to press a button and the thing works, right? So, but anyway, that's kind of how it is. Right, so that's basically PyTorch and TensorFlow came out in about 2016, 17. And now, and the last, you can see one of my last entries here is in 2017, where we got a paper called Transformers. And that's an algorithm that is based on neural networks, but is what made ChatGPT and all that stuff possible. That's the algorithm that they use to build those. But it's just a neural net. I mean, it's really just a neural net, like the perceptron, only way deeper with more elaborate things going on, and they parallelizes really well. Why does it need to parallelize really well? GPUs. So you guys are, this is why I was stressing NumPy, right? You guys have to learn how to program in NumPy. Forget about for loops for everything, because you need to run fast for GPUs. Otherwise, you just can't. If we had a different architecture, quantum computers or something, you'll have to learn how to program for that. I mean, it could happen in your lifetimes, right? That they'll change the hardware and you just got to learn to that. But today we are learning for this that was developed for games in 2000, not very long ago. How many years is 2007? Like 17 years, right? In the last 2 decades, all of this has happened. Got it? Yeah, so that's the history, kind of. The latest development, I guess I would write in here ChatGPT and whatever, but really the last algorithm, major algorithm, is the transformers. That's it. That's the story. All right, so we can stop here for today. On Thursday, we're gonna get into some code.